Guten Tag, Cloud Native Summit Munich. Ich freue mich, heute virtuell dabei zu sein. Vielen Dank an die Organisatoren und das Publikum. That's about it that I'm able to say in German. Hope it was not bad. But just to repeat myself, thank you so much everyone who joins in. It's such a pleasure and honor to stand in front of you, even if virtually, on this gorgeous stage. Today we're going to talk about one of my favorite topics ever. It's about 3+1 way on how to do your MlOps with Kubernetes. So let's cut to the chase and let's begin. And a little bit about me. I'm developer at SolidGate. Also, I was capability pool consultant, platform engineer, and lately my biggest passion ever is MLOps, especially trying to make the threshold into this domain a bit lower. I'm not trying to mess with you. Of course, MLOps is complex, but my strong belief is that if you already know how Kubernetes works and if you have experience with it, you are pretty much equipped to start your first MLOps pipeline and deploy your models. That's why I designed this talk as a lighthouse for you to just navigate these dangerous and dark waters of MLOps. During this session, you will also see some QR codes for different run books that I was preparing. Please use them. I would be extremely happy to see that they actually helped you, because it's always nice to talk about something, but you learn the best when you try to put your hands in it. And let's begin. The first question that we need to think about is what is actually MLOps and why the hell I'm talking about Kubernetes, try and apply Kubernetes to it. Well, we know quite a lot about MLOps, but the three main points that we know about MLOps is following. First, MLOps is complex. Of course, I'm not opening you something like new here. MLOps is tricky domain with a lot of data, the distributed computing, and the amounts of the hardware that we need to use to actually make the training pipelines work enormous. As well, we have second point that MLOps is kind of similar to DevOps, but not quite. I would say that MLOps is very much DevOps on a huge scale, but MLOps also puts to us a little bit different challenges that we used to in classical DevOps. So we are still figuring out the term a bit. And probably MLOps should kind of look like this. Please don't get scared of the picture. The point here is that we have the model and the source code of the model, then we push it somewhere with our favorite continuous integration where we build, test, and package our pipelines. But later we have additional steps because we need to train our model, we need to evaluate it, we need to somehow stream enormous amount of data to make sure that it's actually good, and we have a little bit different approach to storing the versions of model, because versioning in models are not just simple tech. It's also the parameters that were used for training, it's also the additional information for the models that were used under the hood, and etc. etc. So pipeline starts to grow. But please don't get scared with the previous picture. It was my intention a little bit to scare you, but I think that MLOps potentially can be reduced to the formula. Please don't judge it too much because I invented it kind of myself. So when we talk about MLOps, we still have our old good problems. We still need to think about CI/CD, and we still need to think about monitoring, obviously, because we still want to know if our application is live, if the latency is good enough for our consumer to not say hell to you. And also we still need to understand what our application is doing. But here monitoring comes with a little bit a special flavor, because we not only need to understand that our model is alive, we also need to understand that it's actually doing a good job, and we need to evaluate results continuously. So that's the main part that we have here. Later we have additional new parts to the MLOps pipelines that are brand new from the DevOps perspective. First of all, it's IDA. That's where we actually doing exploratory data analysis, and that's where our data comes from, because we need to make our data clean, sanitize them, normalize them, stream it to our pipelines, and make sure that we actually deliver the good data into the pipeline. Because if your model is bad data, it will mess up all the work that you did previously. No fancy algorithms, unfortunately, can fix the bad data perspective. And we also have CT, that's continuous training, and that's the main magic that begins, because here we need quite a lot of resources, but we need to get rid of them quite quickly so we not pollute our bills with extra money. We need to train our model based on some triggers that we can use, but we need to do it quite regularly if you are planning to maintain non-solution. With all of that in mind, I also want to emphasize on the point that, well, even with all of those, we still have 1 million reasons to not use Kubernetes, because most probably you don't need it. If you don't want to train your model continuously, probably you don't need a Kubernetes. You can deploy your model even with cloud builds in Google Cloud. That's basically serverless approach where you can access the GPUs. You can deploy a model on the VM and manage it there as well if you plan to do it static. But in cases when you are sure that your model will be growing with time, when you are sure that you need a training pipeline to run periodically, and we also think that we will have potentially some 2, 3 or more models in our hands that we will need to manage, then yes, we need Kubernetes because it can help us with all of that. Also, if in your team you already have Kubernetes perspective, Kubernetes is worth adding it because Kubernetes are actually created to manage and to scale. So the problem when we need to get rid of the resources and quickly get them back is exactly what Kubernetes was born to solve. And with this in mind, let's start with the 3 ways to do MLOps. I divided into those categories. Basically, you can find a lot of different classifications and different suggestions on how to view things, but I suggest you to check out the following one. Basically, in our modern world, we have 3 ways to do MLOps, and they depend on the level of ownership that you want to have over your infrastructure, over your data, over your models, and over your code. It depends on which expertise you have in a team as well. So from the toughest one where you manage your infrastructure, your model and your code by yourself, to the easiest one where you just use a model as a platform where you can run your pipelines, we are figure out all 3 of them. And let's start with the most infrastructural way, the platform way, where you have the most of ownership. Whenever you hear a platform way in MLOps, that's probably the Kubeflow talking. So Kubeflow, it's a huge ecosystem of tools where you can find the instrument on each part of the MLOps lifecycle. Basically, Kubeflow is cool because essentially it was built with the mindset of Kubernetes in mind. Here we can use the custom resource definitions to prepare the parts that will be put together as a Lego blocks into one MLOps pipeline. For example, if you want to train your model, you can use Kubeflow pipelines where you can put your workers, functions into the containers and then put them into pods, and pods will know how to manage. You can run them all together, run them in a row, in chain, whenever you prefer. Also, here Kubeflow provides us a fancy notebooks that data scientists love so much, and it could be hosted, managed, and used on the Kubeflow platform as well. Also, we have Kserve. That's the place where our model will actually live. Kubeflow is Kubernetes essentially. When you hear one, it means another. So the connections and ease with which you can bring Kubeflow to different ecosystems like Google Cloud, AWS, Azure, it doesn't matter. Kubeflow is Kubernetes essentially, bunch of custom resources that are adapted to the needs of your model. The little problem here is that you are still the one who gonna manage it, because let's imagine the situation with Kubeflow pipelines. So you have your fancy code where you can train your model. Then you can have and build up the component where you will actually put this training function in it. And what happens with it next? It becomes a Docker container that you can put in a pod and run in your cloud whenever you like. But the thing is here that you are still the one who manages the code, you are still the one who manages the pod, and you need to figure out how you will scale it in general. So that's still your problem. Kubeflow just gives you a fancy packaging that you can put it into. Same with the Kubeflow cast serve. Here you can serve your model. That's a simple example, then you can check out on the screen. So basically it allows us to define the image that you want to use under the hood, the amount of the resources that you're going to play around, and as you see, it's essentially the custom resource definition with the inference service name. It allows us to run our cluster on GPUs, TPUs, CPUs, whatever, because under the hood it's still Kubernetes. Also, it allows us to reuse the models, for example, from Hugging Face. If you can just pull your model into the image that is published on Hugging Face platform, then you can reuse it as well here. That's good and that's fun and that's interesting. But let's maybe dig into a little bit easier, cheater way for those one who have worked with Kubernetes and also already have the models that you wanted to push into the cloud without difficulties. And then comes the compute way, because in the world of the Kubeflow, you still need to think a little bit about distributed compute, and you still need to think about how your pod's gonna be scaled, how to make sure that nothing breaks. But with the compute way, and it's a array way, you are stripped of the responsibility over scaling your pods and nodes. So essentially, what is Ray? I will advocate for Ray quite a long time because I love the idea of it, as it allows us to manage low-level resources with a high-level Python API. And everyone who currently put your fingers to the bridge of your nose and say like, oh my god, what we are doing here, low-level processes with a high-level Python API, just give me a minute. I think it's much more better idea than it sounds like. So basically the thing here is that when we talk about models, sooner than later we will face with distributed computing, when we need to make sure that our models that, for example, is divided into separate nodes are actually communicated between parts of itself well, and most of the time we don't want to do that by our hands. And that's why Ray was designed for. It's a framework essentially that covers basically as well full life cycle of the model. Here we can talk about data, about training your model, tuning it, serving it, and as well we have a Ray core. Ray core encapsulates the functionality of the distributed processing manager and stands as a middleman between you and the cloud that you are using. We also have here libraries like Ray Data that I highly recommend you checking out, because Ray Data allows us to stream our data in batches into our training pipeline. So you don't need to load all your training data into memory, and you don't need to pay twice for it. And as well, Ray have a powerful set of tools for the model tuning, LoRa adapters, training, and etc. etc. The main thing about Ray as well, that it's built to be as lightweight as possible. The core idea, if you don't need some leap, you can just ignore it, not implement it into your project, you just use whenever you need. So essentially you can just strip it down to the Ray core. And Ray actually talks more developer logic than infrastructure logic, because here you are using your code to actually navigate how much of resources one component or another component will need. All you need to do to make your array understand your code is to annotate it with the proper annotations, and then array will be wrapped up around your regular classes. And after that, your classes become distributed classes where you can define how much of GPUs are required for one or another class to be used. For example, imagine you can define how much of CPUs your model needs to start, or GPUs as well. You can also put it in the percentage, for example, 0.5 of the GPU is also understandable for Ray. Also, Ray is cloud agnostic. It can be joined in with Google Cloud, AWS, Azure, etc., etc. It doesn't matter. Also, Ray is smart enough to know the difference between CPU, GPU, and TPU, so it's also quite beneficial. As well, you need to remember one thing, because Ray acts here as a scheduler. If there would be not enough of resources in your cluster to be used by Ray, then unfortunately you will end up in the dead loop where Ray will try to allocate resources till it will be actually granted. But that's just a matter configuration, and we just need to make sure that it's valid. But I was talking about Ray and I was talking about Kubernetes, and you may ask yourself, and me of course, well, Kateryna, it sounds so good, but how actually Ray makes sure that Kubernetes know what resources to allocate? Well, good for us, we have Kubernetes. And basically, Kubernetes would be this glue that will connect Kubernetes with Ray by 3 custom resource definitions. That's actually why I allow it so much as well, because Ray is designed to be as simple as possible. Essentially, we have a Ray cluster. That's our main box where all model will live, where we will schedule our jobs, where we will manage our training pipelines. Everything lives in this big black box where the health check, the observability, monitoring, dashboards provided by default. Also, we have a Ray service. That's a custom resource that defines Ray cluster with a Ray serve model running in it. And third, but also interesting one, is Ray job. And Ray job is actually a masterpiece because it allows us to submit the jobs inside of the Ray cluster, for example, like training ones, that after the completion will clean up all the resources that we were using for the training. So you can imagine how nice and easy it is when you care only about training logic, and the cleanup of the resources will be handled by Ray, and you don't need to configure it separately. You just need to use custom resource definitions that are already provided to you. As well, I also suggest you to check out the runbooks that I prepared for running your first MLOps pipeline with Ray. There you can find the code samples and from A to Z how you can configure your Kubernetes cluster to proceed. But for us, it's not the end of the journey. Let's dig deeper and check out the engine way, because this way basically is the way when you are sure that you don't want to do any training, you just want to host your custom model and see how it goes. Engine way basically has different implementations and different suggestions, but I want to talk today about the text generation interface. There is also much more commerce version of it that calls VLLMs. That's basically more commercialized and more configurable tools that you can use, but for the starters, text generation interface, and especially for LLM workflows, it would be perfect one. Basically, what text generation interface is, it's a tool that was provided by the Hugging Face, our famous large language models platform. It is optimized for the deploying your LLM models, and it works like this on slide. So basically, it's a container that already have a web server written in Rust with the most common commands that you can use, that has under the hood a buffer and batcher that will optimize the tokenization for us for pushing the info into our model. And the other part is the actual part where your model is served. That's the model sharding part, where your model could be divided in different shards. That's where the web server sends a request by gRPC. Also, the interesting thing is that here we have a nickel customization. I'm not sure if some of you heard of it, but we'll talk about it in a second, and I'll also explain why it's so important. But if you are questioning it and saying like, okay, it's a really nice picture, but if I plan to put something in production, I'm not sure I understand how it works, and putting something in production that's not clear, it's quite dangerous. So let me walk you through the process. Basically, what Hugging Face suggests that we have a magic with a web server and sharding logic and everything put up into the container, where you need to just provide your model ID from Hugging Face, where you are loaded your model and you're just using some additional model. And you also even can list a list of LoRa adapters, basically the additional extensions to your model to be adjustable. And after that, you just run a container. How simple it is. Well, it sounds simple, but how this magic works and at which cost it comes to us. Well, luckily for you, I already checked it out and checked how it works under the hood. So as I thought, it already consists of few parts. The first part is router that actually accepts the request and makes sure that the data is provided to your model in the best way possible. So here is a tokenization improvements, and etc, etc. Also, we have the model server. That's basically where your model shards live, and here we have a nickel optimization for your models to be able to talk as fast as possible. And the third part that is quite mysterious is the launcher. So that's actually a part that makes sure that everything starts up and bootstraps properly. There is a few different versions of launchers, and you can dig deeper in this topic if you want to, and I highly recommend checking it out. But what about Nickel? Because I talked about it and talked about it. So basically, Nickel is NVIDIA Collective Communication Library, and it's could be explained as super fast communicator between multiple GPUs. Why we need it and why actually bother and why we need to think about it? Well, let's imagine that our fancy model is quite huge, and we don't need to imagine with most of the models. We can think about the models that are like 3.5 billion parameters, 7.5 billion parameters. There is never limit to the amount of parameters that could be used under the hood for the models, and not all of these models could be fitted into one GPU. And basically it's a huge problem because essentially our model is matrix that is using our weights and putting the info through it, then it does the magic with computations and additions, divisions, and etc, etc. But how we can divide the matrix of the weights and then reuse it all together? How it's gonna exchange data? Okay, well, we figured out the way to make sure that we can compute something, but how to not make the pipeline super slow, because, well, as we know, ordinary CUDA is quite slow in these terms. We are pretty stuck in the loop when one machine writes, other tries to read, and it's all just a mess. And that's exactly the problem that Nickel solves. So Nickel acts as a middleman between the GPUs that actually handles the synchronizations and allows us to reuse shared memory most effective way. Yes, so also interesting fact that there is optimization of Nickel, especially on a Google Cloud platform for some types of machine. You can also check it out because it's also adds extra layer of the quicker communication between nodes. And one of the things that in this way TGI handles is a tensor parallelism. So that's what I actually just explained to you. Technique to fit your large models into multiple GPUs and make sure that you're still quick enough to process the requests. If you don't understand anything from this picture, that's fine, because me neither. But if we are walking through the example, let's imagine we have our two fancy GPUs where we need to divide our huge model. And we have shared memory where we can write some parameters, and that's where Nickel will help us. So basically how it works, we have our input layer that is still solid and we don't divide it. Then we divide only inner layers of our model and we split them equally in this case into two GPUs. The input also splits for two GPUs and process it individually on each of them separately, and then concatenated in the end on one main node to be used. That's basically how your data will flow through your model if it is divided, and that's what calls tensor parallelism, and that's the problem that you probably won't even think about, but the TGI already solves it for you and you need to no worry. And also I have a runbook as well. I couldn't leave you without it, where you can check out how to run your first TGI with LLM and to actually even add some LoRa flavors to it. LoRa, it's additional adapters that you can use to make your model more aware of a context and to fine-tune your model a little bit more. And as I already said, we already have 3 ways how to do your MLOps, but nobody forbids us to combine these methods. And that's actually the next point that I want to show you, because nobody said that if you have Ray or we have Kubeflow, they are limited and cannot play in the same playground as each other. Actually, there is quite cool article that I also will share with you in the end, with a real production case from Google, how they found and checked out the together work of Ray and Kubeflow. Basically, in this case, Kubeflow can be the landlord that renders and checks instead of one pod the whole Kubernetes cluster. In this case, we are able to handle the distributed computer in matters of the pods that we are deploying, and we don't need to worry about it. But we still can allow ourselves the comparability and the ease of the building blocks that Kubeflow provides. And actually, as lately now we are in F1 season, I hope some of you are watching it. Let's dig into this example in the Ray Kubeflow and Ray F1 terms. So basically here we can think about Kubeflow as a pit wall. So that's where all the strategies, all the important directions are made. Like a huge orchestrator, or what is happening, it follows the state of all the Kubernetes clusters and make sure that we process them correctly. The headquarters in these terms could be Ray dashboards, where we can actually push the budget schedules and prepare our workflows in general in one scope. Also, we have our Kubernetes operator, and that's exactly the pit crew. So Kubernetes operator will run from our array cluster and nodes to Kubernetes to make sure our model receives those resources that it needs and the scheduling works well. And a padlock, that's a namespace where your Kubernetes cluster could be isolated, because Ray is flat matter of thought, and you need to make sure that you actually have pretty nice guards around it and nobody can use it maliciously. Also, we have analogy with Ray as a high-performance hybrid engine. We have Ray head, Ray workers, and Python API under the hood that allows us to process our pipeline quick and efficient. It allows us to stream our data with our datasets without loading it full into the memory, and allows us to combine the training pipelines in one. And last but not least, the articles that I would suggest you to read, because it's quite cool as well, and I highly recommend you to check it out. So with that, I would say that my talk is ended. Thank you so much for your attention. Please don't hesitate to join to me with LinkedIn. I'm always usually happy to reply and check out new feedbacks. We'll be happy to chat a little bit about MLOps, and also I gave here some examples on the Google Cloud, how the solutions can work. Thanks so much, and let's make our MLOps more understandable and easy to use. See you, bye.